Well, hi, good morning. Thanks so much for joining me in my shop here on July 23rd. It's a hot day here, but nothing like other parts of the world. It's just a regular hot summer's day here. But very hot already this time of the morning. So, but I'm in my nice air-conditioned house. So thinking about this a little bit, my intention earlier was to carry on with the RF side of the receiver. But I was just thinking about it a little more. Maybe I should turn my attention to the output end, the other end of the radio, the end that's driving the speaker. Because there are some protective actions I should really take. It should be done fairly early on in the repair process. And I haven't done any of them, so I thought, well, why don't we do that? I mean, ultimately, I'm going to be replacing all these capacitors. I'm just finding some interesting, what I hope is an interesting way of doing it. So what is it about the output on a radio like this? So there could be a problem in a radio like this, which makes, until it's quite serious, no real apparent change in the sound in the speaker or the operation of the radio. You really can't tell this thing is going wrong. And what it does is, this particular problem, is it causes the output tubes, these two guys here, which you can't see. These two guys there, you can kind of see them down here. It makes them run hot. It run with too much current passing through them. If you turn the volume way up, you might start detecting some distortion while this problem is there. But normally people don't blast their radios, right? They play them at a fairly low level, really. And under those conditions, you can have a problem in this radio, which is causing too much current in the output tubes. And the result of that is you wear out the output tubes prematurely. So it's worth looking into this. You know, often in an old radio like this, you will find the particular capacitors I'm going to hunt down already replaced, because they brought the set in to have the because it didn't have any volume anymore. The output tubes were worn out, and because of these, in particular, these two in this radio, two capacitors that are supposed to protect the tube from it. So to explain this further, we got to look at the schematic. Plus, I got to assess it and figure out where these capacitors are, which ones they are that are in here. There's probably just two of them that are important, maybe more. So we'll look at the output side of the radio. We'll go through it, kind of see how it operates, and then look for these two particular capacitors. Two because there's two output tubes, and this is a push-pull radio. Push-pull. Push-pull. Let me just explain that for a second. When I first heard of this, I didn't believe it. I just couldn't believe it. You could do that with the signal in a push-pull arrangement. Split it apart and put it back together and come up with something that wasn't terribly distorted. So really quick, okay? Here's a tube doing some amplifying. Here's a signal coming in. Okay, and when the signal goes out, it's bigger. I mean, that's pretty simple stuff, right? Coming in, going out. You get one tube's worth of power. Now, what if you wanted two tubes worth of power? You got a bigger speaker, and you need two tubes to produce enough power. This isn't enough. A trick that can be played in the push-pull arrangements. You have two tubes. Okay. I won't go into what's going on over here, but by hook or by crook, you've taken the signal and turned it into this. I'm going to draw this fairly carefully here. And then over here, we've got this part. Excuse my poor sine wave here. So I didn't line these up pretty good. So you see the flat part here. What you really got, if you squeeze these back together, you've got this again. So what's really happened here is the radio has managed to divide the signal, send the top in one direction and send the bottom in another direction. And that's what this radio is doing. Here's the two output tubes. One tube gets the top, so the top comes in, it gets amplified. Sorry, I'm going to have to draw this kind of stupidly like this. And the bottom gets amplified by this tube. So again, excuse my terrible artwork. Ooh, those are some pretty bad sine waves there. But now, there you are. You have the whole signal here, but it's in two pieces, in two circuits. How are you going to put it back together? Very simply, you take a transformer here, hook it up to both of these, bring this out, stick it to ground. So now this signal is going through like this, and this signal is going through like this. Throw some iron in it because it's low frequency. Put another big coil here, catching both sides of this, out to the speaker. Okay, I've simplified it here. There's a little more to it, but this is good enough. Out to the speaker. Believe it or not, this transformer, with the lower half coming in here and the upper half coming in here, can reassemble it into a beautiful, original sine wave if we're working with a sine wave in this. So this is the push-pull. Push and pull. And not, yeah, okay, push and pull is what they call it. Push-pull. How do they get this split? They have another tube. I won't go into the details of it. They have another tube. They have two tubes back here, and the whole signal comes in here, and then they do a little thing, and they do a little thing, and the next thing you know, that's my explanation. You've got the upper half here and the lower half there. One of these tubes will be called an inverter. Inverter. The other tube is usually the last tube in the radio system, if you like. It may not be, but it could be the detector tube. Inside the detector tube are a couple of detector diodes, and then an additional triode amplifier. So really it's the triode amplifier sitting here. There'll be another one down here. Sometimes they use the same tube to make sure everything is the same, to produce the same. So I mean, we want to split these and have one of them higher than the other. So there are those kinds of problems I just mentioned, one higher than the other. Oh, what if this tube is weak and this one's strong? Well, then this part will come out weak. What's that going to sound like? Probably going to sound fairly normal, actually. You may not even pick up on stuff like that. So you've heard a lot about matched pairs of tubes. Well, this is a case where a matched pair might be helpful. Precisely matched? No. You just don't want one running at 50% of its capability while the other one's running at 90. You don't want them that wide apart, but they don't have to be exactly matched. There you are. Push, pull, inverter back here, preamp somewhere in this arrangement, maybe here, maybe another tube here, depends just how they want to design it. And that's the output on this radio. The result is you have the power of two tubes pushing on the speaker. Just one pushing at the bottom, pushing at the top. Another stupid way of saying it. There we are, push-pull. I just can't, I still have trouble believing you can put this back together and get a beautiful sine wave out. So happens some of the distortions that occur right as you cut the tube off match and counter each other. That's why it's, in most cases you're using exactly the same tube in this position. So you get exactly the same distortions, and they kind of cancel each other right at this point. Bizarre, right? Okay, push-pull, here we go. So what's going on in this radio? I can't really, I wish I could spin it around a little easier. Let's look at these tubes. Okay, so these two identical larger tubes are the two output tubes that we're worried about the grid bias being off. This tube is one of the two tubes ahead of it with the triode in it, and there's another one hidden back here. There. This is probably the inverter tube here, whose job is to provide the other half of the signal. Did I say that right? Inverter. Okay, let's look at the schematic now. Take a look at this kind of stuff, and just be aware, I'm giving you my best explanation of this stuff, but I don't know these things 100%. There's a lot to know here, and I'm still young, so I don't know everything. So I could say stuff that's not true, and things like that. So have your thinking cap on when we go through this. I could be leaving lots of stuff out, things I don't even know I'm leaving out, but this is my understanding of it anyway. So let's look at the schematic now. Here it is. The area we're interested in is out here. These four tubes. So here's the two large output tubes here. Here's the tube that's doing the detecting and some preamplification. And this is the inverter tube. Look, they even call it Inverter Tube. The output of these two tubes, if we just trace it very quickly, this one, the output comes along here and goes in on the grid. And this one, of course, doing the same thing with the other half of the signal, coming in on the grid. Now, there are some important capacitors here. The plate of this tube has voltage on it. I'm not sure how much, but some, 100 volts or maybe much more on the plate here. That 100 volts, if you just hook this plate up to the grid over here, the 100 volts will show up on the grid, and that's no good for the tube. You don't want 100 volts. This is a positive voltage, and you want the grid to be negative, maybe 5 or 10, 15 volts, something like that. So to stop the voltage here from affecting the grid, they stick a capacitor here. The capacitor has the interesting capability of stopping DC current, but allowing AC to flow through. And the size of the capacitor and the resistors around it are controlling how much of the audio gets through. Maybe you can cut the bass down. Maybe there's some de-emphasis going on in here. That's what this could be, a de-emphasis capacitor here. The de-emphasis is the system where during recording the treble is cranked way up, and then when you play the recording back, your equipment quietly turns the treble back down. This is happening inside the electronics of your amplifier or your radio receiver, in particular FM receiver. The result of turning the treble back down in the receiver is the hiss and noise goes with it. It also gets turned down. That's basically Dolby noise reduction. Although I'm sure the Dolby noise reduction system is way beyond this kind of stuff now. But originally that's what it was. So this capacitor could be the de-emphasis capacitor, trying to bring down the treble into the we call it the standard range or whatever. So this capacitor here is the one that is very important for stopping the plate voltage DC from getting onto the grid over here. The first thing that happens if you do leak some positive voltage across here and raise the potential of the grid is the amount of negative bias gets reduced. Now, where's the bias coming from? You want the grid to be negative with respect to the cathode. But inside the tube only knows what's going on inside the tube. It doesn't know what's going on outside. So all it needs is to know that the grid is negative relative to the cathode. Now, this is a tough diagram to look at. These two wires here are connected to the heater. This represents the heating element in the tube. And all it's doing is providing heat. It's not doing anything else. This next element is the cathode. This is the one that emits the electrons that are going to flow through the tube. So the cathode can be handled in a couple of different ways. Often they're put to ground, but not in this case. In this case, if we go down here, now this gets a little complicated because it's push-pull and there's two tubes involved. So if we just ignore this one down here, that means we pretend this wire doesn't go any further. And you'll see that the cathode reaches ground through a resistor, a 2-watt resistor, 2 watts. Dissipated heat here. 2-watt resistor, eh? Well, in fact, it's carrying the current of both tubes. So the through current in the tube, and I'm going to draw it this, I'm going to show it this way, comes up, is burned off the cathode, or boiled off is the term people like to use, boiled off the cathode, and then the plate here at a high positive voltage attracts the negative electrons through the tube. This is the model that we all see and use all the time. Of course, it's not really quite correct. It's not really like that. It's a little more nuanced, just how the electrons are moving inside the tube, and I won't get into that. So this current is flowing through this resistor. It's causing a voltage drop on the resistor, and this is causing the cathode voltage to be somewhat positive. Maybe 10 or 15 volts positive. That's what the drop is here. Something like that. Well, that 10 or 15 volts positive makes the cathode look positive to the grid. The grid voltage is essentially zero. See, it's just grounded through this resistor. Grounded through this resistor here. So there should be essentially zero DC voltage on this grid. There might be a little bit of negative voltage there for reasons I won't go into. But if it's positive relative to ground, then this capacitor is leaking. So there's another capacitor right there. So wouldn't that block it? You know, this is a 0.01, probably a paper capacitor, and this is a 270 picofarad, probably a mica capacitor. Probably this capacitor is fine. Probably this guy is leaking. Probably. You don't need to leak much charge through it to start changing the voltage of the grid here. This is a fairly large resistor, so the flow of electrons is restricted through these two resistors actually. So they can kind of build up some pressure here, some negative pressure from electrons. How are they getting through this capacitor? Well, look at this little deal here. This is the tone control, bass tone control. So, you know, with a capacitor, the high frequencies get through easy, the low frequencies struggle through a capacitor, and it has a lot to do with the size of the capacitor and the resistor circuit around it, causing a filtering sort of effect, or a controlling the filter effect, I guess you could say, the size of these resistors and that. Why did I bring that up? Because let's suppose this control is slid all. This is a moving thing, right? This is the tone control, bass tone control on the front of the set is sliding this thing back and forth across this resistor. If you slide it over here, what has happened now is you have a short from here, whoops, through this to here. So you've just bypassed. You've just gone right around this capacitor. Now, if you slide the control back, you're increasing the resistance of this path and making it more attractive for signals to work their way through this capacitor. What will come out the other end of this capacitor is something lacking a bit of bass. So more bass, put this down here, everything goes through. Slide it up here, now big resistor here, forcing the signal through this capacitor and depleting the bass. I explained that very well. I hope I did. So that's what's going on here. So I tend to keep the bass turned up pretty high. I think most people do. So this would be down this way. You could just forget about this capacitor. If this guy is leaking, it's going to leak right through to here, and we're going to find a positive voltage relative to the chassis sitting on these grids, which is not good. So that's test number one. What is the grid potential? Maybe it's test number two. What is the grid potential relative to the chassis? Is it zero, or has it gone high because of a leaky capacitor? That's the question. Maybe the first question is, what is the voltage drop across this resistor? 220 ohms, 2 watts. The 2 watts indicates this is a resistor that probably runs hot. Hot resistors wear out. Yeah, try to stay cool during your life, and you'll live long. Let yourself get hot too much, and you're going to burn out early. So now there's something kind of interesting here. So the cathodes are grounded through this resistor, but what's this wire doing here? This wire comes down and it gets into the power supply filter capacitor. What's happening there? So if you notice, this is one device. This is one part here. The Molinode condenser. I guess Molinode must be a company. So they packed all these into one, and then they sell them to the radio manufacturers. Hey, buy our 4-part capacitor. 3 of the parts you can use as high voltage filters, and we threw in another part, this one here we're going to talk about in a minute. So look, 400 volts, 300 volts, 450 volts, these capacitors here can withstand a fair bit of voltage. Not this guy, he's only 25 volts. What's he even doing in the package? Because the capacitor manufacturers know that in most radios, a capacitor of this size is needed to bypass this resistor. Oops. Now the bypassing of this resistor is a little bit tricky to understand. There's a couple ways of looking at it. One is you're trying to provide a signal ground for the AC circuit up here, but you have this resistor in the way. If you just left the resistor here as it is and forgot about this connection to that capacitor down there, then all the signal, including like all the audio signal, would be passing through this resistor, and this resistor is going to burn up some of the energy. The actual signal you're trying to get out of the speaker is going to end up losing a bit on this resistor. If you bypass it, just go around it with a capacitor like this one, see, this is a pretty large one, 20 microfarads, 25 volt. The signal will choose the capacitor. The DC circuit is different. The DC circuit will continue to go through here, but the AC circuit, signal circuit, will go down here, and you will eventually, it essentially provided an AC or signal ground right on here. The effect of that is whatever this tube is doing is showing up in this coil. There's nothing wasting power, wasting its output, if you like, here. The other way of looking at it is the bypass is really enabling the signal that's applied to the grid to be applied between the grid and the cathode. If you don't have a bypass, then you're kind of supplying the grid signal between the grid, this resistor, and the cathode. And so the grid signal itself is lost to some degree in this resistor. And then there's also a, the direction of the current flow is reversed as you go through a tube. So what's happening on the grid, the opposite is happening in the output part of the tube, and the two of them kind of clash, and the result is, again, a reduction in output. So I won't explain that any better. There's lots of stuff written about this, and although I read it regularly, I just can't keep it all in my head. My head isn't that big. It really isn't. So another test here then. What is the voltage at this point? The voltage right at this point, which would be positive relative to the chassis, is actually the bias of the tube. Instead of pushing the grid negative, push the cathode positive to get the same effect. The problem with radios like this, another problem, is this resistor often goes high. Because it's working hard, it's hot, it goes from 220 to maybe 500. At that point, you're over biasing this tube, and you're going to hear distortion and other crappy sounds coming out of the speaker and the like. In the worst case, I guess that thing can open right up. If that resistor opens up, you won't hear anything. I'm pretty sure you won't hear a thing coming out of the speaker. And it happens. These guys open up. If this capacitor wears out down here, then some of the signal will be lost. But you probably won't know it because you're just going to advance the volume control another few degrees. Right? Volume control solves all ills in a radio. Well, maybe not all, but most. Okay, so that's the name of the game today. Today is going to be read this voltage and read the grid voltage on the two tubes. Good. Coffee break time has come. Okay, next thing we've got to do is identify a few of these parts. So this is the rectifier tube down here, and the two output tubes are here and here. And that schmozzle, which is very, very hard to look at, I know. So, do you see a big fat resistor anywhere in that area? Oh, look, there's one right there. This is probably the cathode resistor. So without checking it, I'm going to go on the assumption. Cathode resistor right down to the chassis here. Now, this has got to be connected somehow to both tubes. So we see it's soldered to one tube, and then it's very hard to see, but there's a wire here that skips up to the other tube and connects to the same pin. I think these two tubes are in exactly the same way. Yes, they are. In other words, the key on these tubes is pointing exactly the same direction, so the pin layout is exactly the same. So here we are. So this is the cathode here. You can see a wire going up. Where's that wire going? It's going over to the Mulliner, or whatever this thing is called. This is the main capacitor here. Again, it's a little hard to see. It's got 4 terminals. 3 of them are busy working with the power supply itself, or perhaps other things I'm not aware of. I think they're just filtering the power supply. And this one is the low voltage one. That's funny. I just heard my yeah, okay, right. I just heard a cat bell ringing in my house, and I thought both cats were outside, but no. Okay, small distraction. So here's a good test point. This point should show up as the bias voltage 10 or 15 volts positive to the chassis here. So that takes care of that. That's easy to do. Test right there. Now, another question would be the grid. Where's the grid? So the grid is on pin number 5. So we just pick this tube because it's easier to see. And there's the key. 5. 1, 2, 3, 4, 5. This looks like 5 here. 5 here. There's a small capacitor right there. Did I count it right? Let's try it again. 1, 2, 3, 4, 5. This is 5. So that's a grid, and then likewise the grid would be down here. We just count again. 1, 2, 3, 4, 5. This capacitor is right on that grid. 0.01. 0.01 on that grid. Why not the other one? Why is there not a capacitor like this on the other one? I'm just going to peek at the schematic here myself and tell you that the capacitor that's supposed to block the plate voltage from the grid, the plate voltage of the succeeding tube, the tube ahead, 0.01. So there's a 0.01. That's a 0.05. That's a 0.005. That's a I don't know what that is. That's a I don't know what that is. And this is a looks like 0.005 on here. Where's the other 0.01? Well, I guess my process of elimination. So it's either this guy, who appears to be connected to the so this one is connected to a shielded cable. No, that's something completely different going on. It must be this one. Okay, it's not quite adding up here. So again, let's start with pin 5 on the lower tube. Pin 5, count 1, 2, 3, 4, 5. 5 gives us this capacitor without a doubt. And that matches the matches it. And then remember, this is the tube that's the inverter tube. So this is the inverted signal coming here, the lower half, or maybe not, but you could think of it as a lower half coming through here, getting to the output tube. The same thing should be happening up here. How come I don't see a similar capacitor here? I see this one. Got the right tube, yeah. Shouldn't there be a 0.01 coming here? And it's just a little one. Oh, is there another little one on the other one? And there is. There's a little one. Well, I'm just not seeing it. I'm just not. How can I not see it? I'm looking right at the radio here. So let's look at this resistor. Right across the radio. So this is probably the signal coming in to one of the two. That doesn't make sense. Take it back. I'll swallow my words before I finish them. You got me. It's not what's going on here. Count again. Did I count them wrong? Let's just be absolutely sure. 1, 2, 3, 4, 5. 5 is the grid. Did I miss something on the schematic? How this is done? I'm sure I saw 2.01s. Capacitor's missing? No. Well, what is hooked up to this pin? The pin we're interested in has this resistor hooked up. It's coming way over to here. And this point 0, pretty sure it's 0.005. That's going off to this inverter tube. Something funny going on here. Something funny. Let's revert back to the schematic and take another look at that. So I found one of these 0.01s. Now isn't there another one down here? 0.01 right there. How can you affect the tone? Yeah, sure. Let me affect the tone. Yeah, let me just finish off with this. Let me affect the tone by controlling what's happening with one tube when there's two tubes. That's curious. It's not that it's a stereo. It's not stereo in any way at all. Well, I have to find this capacitor. So, you know, it's probably installed out on the end of a wire related to this resistor. 270,000 half water, 270,000 on the grid, and 270,000 on the grid. Okay, let me look for those, and then we'll just keep hunting for this thing. So 270 would be red. What's a 7? What's a 7? I think I know that. 7. Show me a 7. What is the color of 7? Purple. Uh-oh. Pin 5. The resistor, oh, it's just buried right here. I'm not going to be able to read that one. Oh my gosh, I see red on it though. So 270 is going to start with a red one. This is 270. This one here. But maybe not. Maybe these colors have changed. This looks like 27K is what this looks like. It's supposed to be on here. Well, this is what is connected on there. Come on. So I like to be certain of things before I go ahead. And again, if you don't. Hey, here's something I've learned in life. Listen to this. Investigations proceed until the investigators are satisfied, not until the truth is known. Now, it may be that they're satisfied and they have the truth. Maybe. But generally speaking, investigations stop when the investigators are satisfied. So it's pretty easy to get satisfied prematurely. So what have we got here? What am I doing? I'm across a resistor and I'm getting a capacitance reading. Yeah, that didn't work. let's try a more typical ohm meter here. So if there is a capacitor there, this ohm meter won't care if there's a capacitor in parallel or something. I'm looking for 270K. Right here. Does it tell me 270? 280. So, you know, that's 280, 270, same thing. The other resistor should look just like this. A little puny guy. Well, something's not adding up here at all. What's this resistor? I'm across it. 24 ohms. How about this one? This guy checks in at 63. No, isn't that 63K? Okay, now let's find out. Yeah, 63K. That's what that was. Body and dot. Green is 5, isn't it? Body and dot be 5. Yeah, this one I tried to figure out before, and I'm not sure if there's a color here or not. Any other resistors in there? Well, there's this big one. We should check this. Yeah, not on the 600,000 scale. This one's 200 and something, right? 220 was it? $222. So it's good. Look, it looks good. It is good. That's good. Of course, this is bypassed by this capacitor up here, which I'm not so sure we can really check it. Can we? Can we check that? Let's try it with this. And to the chassis. Well, it's taking its time, because I guess it takes a lot to charge one of these, maybe? Is that what it is? 27 picofarads. Wow, that's nothing at all. that's nothing. That indicates nothing. Nothing is there. I don't know what to make of that. Crazy test. Because the radio is largely operating, you can't expect things to be terribly wrong in it. Where are we getting to? We're still trying to hunt down the other 0.01. And one of these capacitors looks a lot like that one that burned up back here, this thing here. You have two capacitors on the same pin. This is, just go over them again. This is 0.05, 0.01, looks like 0.005, and this guy's hooked up to a, what is he hooked up to? Oh, that's not a shielded cable. That's crazy tape on there. To this wire going down here to this terminal, which is then going over to one of the tone controls. What have they done here? It's very strange looking. Let me just get the other camera because it's kind of weird looking. You know, small things fascinate me. But you never know when the small thing turns out to be a very important observation. So we're looking at this capacitor here. what is going on there? So it looks like friction tape. And behind this old guy here. Could nip this guy off. I want to do this in order though. Any value on there? I can't see the value. It's hidden away. So it's on a wire that's this wire here. It's pretty weird, eh? Like down, under, back up, friction tape, and it's kind of hanging here. It's not quite the normal procedure in building radios. So we get this wire, where's it going? It goes to this terminal strip. And from there, it follows on this wire all the way out to the tone control. The tone control. That's right, it's not D. There's one here and there's one here. There's a capacitor hidden underneath the tone control. It's another good looker. Where are you, Mr. .01? It's a egregious looking capacitors. I know, I can hear you. Just change them, change them all, change them. Well, why don't we do this? We'll do the testing, the before testing, and maybe along the way I'll make something will get clarified or something like that. Okay, let's do that. Let's do that. Let me just get this out of here. Now the meter we're going to use is this guy here. I'm going to practice before I turn it on. I had identified the pins and now I think I've forgotten them. So here's the bypass voltage measured here. We should see plus 10, 15 volts, something like that. Grid voltages are tricky to measure because there's not much charge on the circuit, so when you apply the meter, it draws some of the charge away. So what can happen here is, if some charge is built up on the grid, and the grid is actually running somewhat positive because of a leaky capacitor, you put the meter on it, and the meter will go whoo, like this. It starts going up, but the charge is bled off through the meter, and the next thing you know, it's back down here again. So you look for the pop-up. Can't get a quantitative reading, but at least you know, yes, there's a charge building up there. Now if the meter's impedance is high enough, then the charge bleeds off slower, so you can see it better. And this is a good meter. That's why I'm using a vacuum tube voltmeter here to do this. So the two grids, the one is here. We would expect to see 0 or slightly negative. And the other one would be in the same position. Oh, it's on the end of this capacitor, right in here. Okay, I'm ready. I am ready. And we can even measure the plate voltages, which are on pins 3. Pins 3. Okay, feeling the key. 1, 2, 3. Wow, this guy. And one, two, three. So you see piles of capacitors. There's a capacitor connected right between the two plates. There's a capacitor connected between the two plates. Let's just once again jump on the schematic and look at that. So yeah, there it is. There's the capacitor between the two plates. Look at the voltage on it. 800 volts. Yow, I don't have an 800 volt capacitor. Mine are 630 volt. But they'll probably do the job fine. But 800, isn't that scary? You gotta wonder, 800, how do you get 800? Some wild oscillation in here or something? Perhaps. But I notice the capacitor in this position is often very highly rated. Okay. Okay, so this is on positive 50 volt scale. Radio's plugged in, speakers connected, no antenna, volume down, tones in the middle. Turning it on, it's not powered up yet, tone in the middle. There we go. Dim bulbs behaving normally. Radio's on broadcast band. Volume's up a little bit. We'll wait now. Everybody stand back. Here it comes. Clicking and popping. A little dirt in here, but the tone controls are doing their thing. We don't need to listen to it, so we're going to turn the volume down. It's good volume too. Okay, first one we want to look at is the cathode voltage, and we'll find that on here. Watch the meter now. You can't watch the meter. I'm going to move the camera. Watch the meter now. Here we go. 10 volts. The actual voltage is 15 volt scale. Just about 15 volts. That's perfectly fine. How do we know that's perfectly fine? Because we look in the tube manual. 6F6, 6F6, EFG. This will give maximum ratings and typical operational ratings. So typical operation, and this is also in push-pull. Now they're probably just going to give a grid resistor value. Cathode bias resistor, 320. So in this radio it's 220, it's not 320. You know, the engineers make their decisions on what they want. It has to do with how much B plus is up on the tube and other stuff. So they've come up with a different number, but it's not going to give me a grid voltage here, will it? I don't think so. It gives you a plate current, which is very hard to measure. So we're not going to get it on the push-pull. But if we look up here in typical operation where it's not in push-pull, it's just a straight-through amplifier, we'll probably find it here. No. Yeah. No. Control, grid number 1, control voltage, minus 16 volts with 250 on the plate, minus 20 volts, 285, and what did we measure? We measured something right in that range. Okay, so it's within the range. I mean, it's not unreasonable. Now, the question though is, what's happening on the grids? Are the grids floating high because of a leak? So the grid is 5. Remember all this now, Jim. All that practice. Pin 5. So I think we'll put this on negative. So the meter, when it goes upscale, it's reading a negative voltage now. We're still on 15. No idea what we're going to see here. Probably not much. Here we go. I think this is the grid. We should hear this coming out of the speaker too. There's nothing going on over here. What am I doing? I'm doing something wrong here for sure. Something must be going wrong. We'll do the other grid. The other grid is on this capacitor. Stick my probe in there. That's what men like to do, by the way. Here we go. Nothing. Well, that's actually a good sign, isn't it? Yes, it's a good sign. I'll put this back on positive because it's actually a positive voltage I'm looking for. Just zero my meter better. Okay, now I got my head straight too. Assuming this is the grid. No sound. It's very strange. We have a tiny positive voltage there. Tiny. We're talking like 0.05 volts or something. Tiny like that. And on the other grid, just a wee bit higher. So we got 15 volts from the cathode resistor, and then you've got 0.05 volts going the other way because of the leak. It's nothing. So the suggestion here is the two blocking capacitors, only one of which I can find so far, are doing their job. Everything's good. Everything's good here. There's no disaster, quiet disaster happening. The cathode resistor's good. Coffee break time. That's what it is. Coffee break time. Yeah. And I'll just take a moment and show you how I deal with the problem of capacitors all mixed up in there. How you're going to change those out without getting confused. And that's a challenge for me. I don't know about you, but for me, getting confused doing this stuff, it just happens so easily. So what I do is if I'm going to remove a capacitor from here, before I install the replacement, I'll put clip leads where it came from. And in fact, in this case, I still have the capacitor sitting here. So what I've had to do is I had to kind of remove the upper layers of parts to get to the bottom. Here's the bottom part down here. So you can see one here, I've cut one end off and I put a clip lead on to show where it's going. Because I know myself, I know what will happen. It will turn around, say hello to my cat, and when I turn back to the radio, I'll have no clue where things came from and where they're supposed to go. So we're going to go after this guy to start with down here. He's on the green clip. Okay, I also clip these out so a little bit of wire stays behind. It's a very, very small amount in this case. So I can spot the wire, the wire I left behind, and then know where the part came from. And often you use that wire to connect to anyway. Clip this guy out. .05. Okay, 0.05. Just carry on here. Okay, I'm down to one last capacitor. That's this one with the weird wire thing happening here. Now, why would they do this? This is really a strange looking thing. Why not just lay the capacitor with the long leads between it? Why did they do this? What's this take? Let's put this little piece of wire here. There's something more to this. You know what? I can cut out the one end and extract it from the radio. We'll take a look at it. Better look at it. Okay. Just mark this. Why would, like, this is not factory stuff here. You don't. It's soldered nicely. Hey, this is the .01. It's not going to the grid though. It's going to some other terminal. What terminal is it going to there? Did I count these terminals wrong? Wait a minute, this is a different tube. It's a .01, but it's going to a different tube. Well, I think I'll just maintain this. Kind of crazy way of doing it. That's really bad, because it's right in next to the chassis here. Generate a short circuit. That's why they put the friction tape on it. By the way, friction tape's very good stuff, because you saw me take it off. It's pretty much the same state it was the day they put it on. Pretty much. Try that with some of this vinyl tape. No. Vinyl tape is crappy. Well, let's just cut it off. Stick another .01. I never did spot at .01. You know what? This is .01 to here. Then it's through this capacitor to the terminal. And that's what was shown with the tone control. So that's what's happening. So this is the other .01. That's what's happening there. Okay, we'll install that, and we're just about ready to test the radio and see if I messed it up. Okay. Now, just double check everything here. Make sure everything is, I didn't miss any solder connections. That's a lot of capacitors to change all at once. You see I put a shrink sleeve on that flying joint there. Decided to follow exactly the wiring that they used. I don't think it's impactful down here. I don't think the wiring is quite so critical. You can pick up a hum if you run a grid wire really close to the power wire or something like that. It's up in this part of the radio where you don't want to be relocating parts, and you don't want to be utilizing alternate points of ground and all this kind of stuff, or you might find out that your radio oscillates when you're done. Goodness knows why. Okay, I think I've done it. I don't think I made any mistakes. There was a moment there where I literally broke out in a sweat when I thought I had confused a couple things, but I don't think so. Make sure there's no shorts in here. It would be better to do a couple capacitors and then test the radio, a couple more and then test again. That's too much excess wire there. It's good. It's good to go. Okay, we're ready to test. Does it work? It will probably work exactly the same as it did. So hey, everybody back up. Stand back. Stand back and stand by. So I'm going to watch those dim lights. I've made lots of changes. Some of them are on the plate circuits. So dim bulb very important. Any reason I should hesitate? Volume down a bit. And we're on broadcast. Okay, here we go. Dim bulbs, what do you tell me? Tell me everything's good. The bulbs are saying it's all good. There's no B plus yet. So we'll just keep an eye on that light bulb there. And give the radio quite a bit of time to warm up. 86 volts. There's no B plus until the rectifier heats up and starts doing its job. And under 85 volts takes a long time. So you can see the dim bulb's getting a little bit dimmer, and then they should start brightening up. They're getting dimmer. I'm getting dimmer. That's what's happening. There it is. Full volume, you can hear it. I'd say we're good to go. Okay, volume down, full power. Stand back. Smoke. No smoke. Tone seems to be more controllable. We still have a tone capacitor here I left. I'd say there's a pounding hum in there. Maybe a 60 cycle hum in there. Okay, but radio is working. One thing we could hope for is an increase in volume. A little hard to judge. Let me dial in some noise here. I think it's the same volume. Lots there. Very good. I survived. It survived. We both survived. You survived too. Okay, so that's it for today. Obviously, I'm going to get outside. My cats are wondering where I am. So I'm going to get out there and enjoy the day, and you should do the same. See ya. Bye.